Good day and welcome back for the third and final installment discussing the limit of a function. We left off in our second video discussing one-sided limits. That would be the limit of a function from the left and a limit of a function from the right. And we mentioned this useful property that we have at the top of the page. And I'm going to use that as a starting point for this video as well. So what we saw is that if the limit of a function is equal to L, so intuitively for inputs close to A, the outputs of the function will be close to L. That is true if and only if the limit from the left is equal to L and the limit from the right is equal to L. That is for inputs close to A but on the left-hand side, F is close to L, or inputs of x close to A on the right-hand side, f of x is also close to L. And the key observation we made previously, and is worth making again, this gives us a very convenient way of sometimes showing that a limit does not exist. So note, if the limit as we approach A from the left is not equal to the limit as we approach A from the right, then the limit itself cannot possibly exist. So that would be the limit as x approaches A of the function does not exist. And this is a point where if we were working together in person, I would have you turn your desks or your chairs and work with your neighbors for a few minutes to look at this graph and determining the following limits and function values. And since we're unable to do that, what I would like you to do is to pause the video for a minute or two, whatever it takes, and go ahead and fill in all of these values. Okay, assuming that you've paused your videos and you've filled in these values, and remember, if you haven't done so, I would strongly encourage you to do so. And the reason I will ask you to do this occasionally is just to try to make this as active as possible. You taking the time to think about it will help you better understand the material. So let's see here. Let's go ahead and first fill in the function values. So f of 1, f of 2, and f of 3. So f of 1 would correspond to this closed circle. So f of 1 is 1. F of 2 would correspond to the closed circle here, so that would be 4. And f of 3 would correspond to the closed circle at the point 3, 2. And let's go ahead and look at some limits. So the limit as x approaches 1. So we think for an input of x close to 1 on either side, but not equal to 1, the outputs will be close to 3. And that's true from either side. Next, we have the limit as x approaches 2 from the left. So we're thinking for an input close to 2 but on the left-hand side, what are those outputs going to be close to? So if we're close to 2 on the left, we see that the function outputs appear to be getting closer and closer to 4. And then now I'll stop kind of tracing through with the graph, but I'll go through it a bit more intuitively. If we're close to 2 on the right, our function outputs look as though they are close to 3. So the limit as x approaches 2 from the right is 3. And note, that indicates for us immediately the limit as x approaches 2 does not exist. And just so there's no confusion, we're using the above property. The limit as x approaches 2 from the left is 4, which we can all agree is not 3, which is the limit as x approaches 2 from the right. Therefore, the limit as x approaches 2 does not exist. And lastly, for an input close to 3, whether you're on the right side or the left side, those outputs appear to be getting closer and closer to 1. And recall when we are talking about limits, it does not matter what happens at that value A. So it does not matter whether the function is defined at 3 or has a value different from the limit. And I'd like to finish up our discussion with one additional example. So in this example, we would like to investigate the limit as x approaches 0 of the function sine of pi over x. And note right away that sine of pi over x is undefined at x equals 0. But note there's no issues whatsoever with that, because when we take the limit as x approaches 0, we substitute in values close to, but not equal to 0. And since this is our first time encountering a trig function in our course, I thought it'd be worth taking a moment and just sketching out kind of what the graph looks like and noting a few key values. And you may recall from your extensive experience with trig functions that sine of n pi is equal to 0. And note in our case here we're thinking n is a whole number, could be positive or negative. And similarly, you know that sine of pi over 2 is 1. But you also most likely recall that the trig functions are periodic with period 2 pi. So sine of pi over 2 plus 2n pi will be equal to 1, where n is any whole number. So we know that at 0, the sine function is 0. Similarly, pi, 2 pi, minus 2 pi. It's equal to 1 at pi over 2, and then if we go 2 pi in any direction, sine of minus pi over 2 is minus 1, as is sine of positive 3 pi over 2. And now we kind of just intelligently connect the dots, and we get the sine function that you all have worked with most likely many times in the past. It oscillates back and forth indefinitely between plus and minus 1. So there are infinitely many inputs where you have 0 as an output. And then likewise, there's infinitely many inputs where you have plus 1 or minus 1 as outputs. So let's turn our attention back to this function f of x, which is sine of pi over x. And what we would like to do is kind of get a little bit of data and think, if we plug in inputs close to 0, what are those associated outputs going to be close to? And one way to plug in something close to 0 is to start farther away, like 1, get closer, 1/2, 1/3, 1/10, 1 over 100. Note, as we divide by bigger and bigger numbers, we get closer and closer to 0. So these inputs that we are plugging in, the 1 over n, those are getting really small, i.e. really close to 0. So this table of values should give us some good anecdotal evidence as to what we expect the value of this limit to be if it exists. So note, if we substitute in 1, we would have sine of pi over 1. So we have f of 1 is sine of pi over 1, which is sine of pi, which we've set above is 0. F of 1/2, just substituting this in, would be sine of pi over 1/2, and dividing by a fraction is multiplying by its reciprocal. Sine of 2 pi is also 0. And notice all of these inputs have a very similar form. In general, we're thinking something like f of 1 over n, which is sine of pi divided by 1 over n, which multiplying by that reciprocal makes it sine of n pi, which we observed above is 0. So as we substitute in these inputs, getting closer and closer to 0, all of those associated outputs are becoming closer to 0. And with this in mind, we now have a guess. the limit as x approaches 0 of sine of pi over x, we think could potentially be what number? And I want you to take 10 seconds, 15 seconds, and write down what is your guess for the value of this limit. And hopefully you've written down a guess, and hopefully it's not hard. I've led you in the right direction here with our table. All of those outputs are 0 as you approach 0. So our guess is for inputs close to 0, the outputs of the function should also be close to 0. But it turns out that the limit in this case actually does not exist. As we approach 0 using very specific inputs, we can make sure that the output would always be 0. But we could tweak these inputs slightly so that we have infinitely many spots as we approach 0 where the output is actually 1. And if you go to your textbook and look at a picture, so figure 7 on page 54 goes over this specific example, and it has a nice graph of the function. And what we are hoping to illustrate in this example is just the limitations of trying to evaluate a limit by just making a table of values. It can be misleading as it is in this example. So I'm going to put a little line through this, and I'm just going to note that it turns out the limit as x approaches 0 of sine of pi over x actually does not exist. And what this is indicating for us is we are going to want maybe a better approach, something that's more definitive, something that is very systematic and methodical. And that's what we are going to investigate in our next section when we introduce the limit laws. So stay tuned and take care.